Uh, okay, we meet again. Okay, I want to continue from our first part of the fundamental and concept and theories in XRD analysis. Okay, for this second part, I will explain about the XRD machine itself, and then the theory and fundamental involved in XRD uh, measurements. Okay, this slide shows the assembly of the XRD machine. Okay, see my mouse. Okay, the left side is the X-ray tube, the middle part is the sample holder, and then the third part is the detector. Okay, so for XRD machine, okay, normally not normally normally the X-ray light or sources, okay, will generate in this X-ray tube, and then this X-ray tube will generate the X-ray wavelength. Okay, due to the copper, depends on the metal plate you use as to generate the X-ray sources, and then this X-ray wavelength will bombard the sample on top of the sample holder, and then this sample holder, the wavelength that pass through the sample will reflect back or diffract back and then detect by the detector. Okay, the pattern as I mentioned in the first part, okay, will be detected by the detector. Okay, detector. Okay, so this one is the actual setup in our laboratory for XRD machine. Okay, this left side from my screen, okay, is the X-ray sources. Okay, and then this one the detector, and then this one sample holder or sample stage. Okay, uh, for this measurement, for XRD measurement, normally we can do a few type of specimens, okay, to measure. Number one, of course, the most common one is the powder form. Number two, we can use as a thin film. Okay, thin film. Number three is you can use a solid sample. Okay, solid sample. And number four, normally we can use liquid, but liquid we don't have the the sample holder for the liquid. Okay, this thin film we can use the thin film. Okay, but later on, if you move to more higher level of years, let's say you went to third year and final year, definitely you will use this kind of measurement. Okay, so you need to understand how this XRD machine work. Same as I mentioned in the top image. Okay, in the top figure, the X-ray will come from these X-ray sources as the left side, bombard the sample surface, and then this wavelength generated from the X-ray tube will diffract back and detect by the detector. Okay, bear in mind when you do this measurement, okay, this X-ray sources and detector will move simultaneously according to the angle. Okay, let's say I let's say you have like this. Okay, let's say this one how can I say 45 degree. Okay, when you do the measurement, okay, so this measurement for XRD normally we can measure up to 90 degrees. So meaning that start from zero like this. Okay, I cannot fold more my hand. Okay, they will move slowly, 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 slowly until they get 90 degree. Okay, 90 degree like this. Okay, so uh, later on I will show in the video. Okay, I will post in this e-learning the video how our XRD machine in laboratory works. Okay, so how this XRD machine works. Okay, as I mentioned earlier, okay, in my video, okay, XRD we can measure only for the crystalline materials. Okay, uh, normally we can need to measure the crystalline materials. Okay, so how we want to do this? Okay, let's say you have powder. Okay, powder form in as a 3D form, right? So how you want to see the whole patterns of uh, the solid that you measures. Okay, so in this uh, slides, okay, shows that Imagine you have the crystalline material as a 3D form, and then you need to fold it until you get the 2D view to see the pattern. Okay, in this case, from this globe, you want to observe where is Malaysia, where is the UK, where is the Sweden, where is the Czech Republic, and others country. So from this globe, you can find it by rotating it, but actually we want to see the overall of the world by only in the single layout in 3D or in 2D form. So therefore you need to do this kind of analysis. Okay, so in XRD measurement, we have we use the Bragg's law equation. What is the Bragg's law? I think you need to find by your own. You need to discuss it in your lab report. What is the importance of Bragg's law in XRD measurement? Okay, here is the equation for Bragg's law. Okay, 2D sin theta equal to lambda. Okay, lambda is what? Lambda is known as the wavelength of the X-ray sources. Theta, what is the theta? Theta is the diffraction or reflection angle from the input and output of the wavelength. Okay, D is what? D is the we call as a spacing between the lattice plane. As I mentioned earlier in my video, normally we call D as a interplanar spacing. Okay, because for crystalline materials, okay, the atom will arrange in the stacking order. So therefore, each layer of these atoms, okay, between them has a plane. Okay, how I want to imagine. Okay, so you have, let's say you have one piece of paper. Okay, one piece of paper. On top of the paper, you put some circle representing the atoms of the material. And then in order to get a crystalline material or solid material, you need to form many layer of the plane like this. Okay, so meaning that maybe from, let's say for example, you have one material that has solid. So in this solid material, you have 100 layer of planes containing many atoms. So between this plane like this, okay, we call as a interplanar spacing. Okay, why I want to express this? Because in the next exercise, for your lab report, for your exercises, for your question, okay, we will use a lot of this D value. Okay, so please make sure that you understand what each symbol represent is. Okay, because you need to elaborate it, you need to find it, you need to explain it. Okay, it's easy for this equation. Let's say we change the D value, of course. Let's say the lambda is constant. What happened to the, let's say if the lambda is constant, what happened to the D value when we increase the angle of reflection? What happened? Okay, this one you need to think by your own. Okay, because this one might be come up from the test later on at the end of the semester. Okay, here is the schematic diagram. I would say how the pattern is produced from the XRD measurement. Okay, so in this case, imagine you have this kind of wavelength. Okay, imagine this one the sample stage. Okay, the sample stage containing sample, and then using the Bragg's law equation, when the lambda from the X-ray source is constant, this lambda will bombard the specimen surface, and they will diffract at different angles. Okay, so meaning that this kind of layer of planes, okay, stacking each other, and then this gap, okay, when the light pass through, okay, they will produce the scattered of the pattern intensity. Okay, as you can see here, when we short the light here, so when have this media or the sample, they can be diffracted here. Okay, so based on this Bragg's law and this principle, okay, from the XRD measurement, okay, as I mentioned in this slide, okay, when you move the X-ray source angle, the detector as well will increase the angle simultaneously. So therefore, in order to explain this diagram, okay, this y-axis represent the intensity or how many counts they will detect for each angle that scanned by the wavelength. Okay, for example, imagine you have this specimen. Okay, later I will explain. Okay, so meaning that when you bombard the wavelength, okay, on the surface, they will give you a pattern like this. This one we call as a diffractogram for XRD. So remember, each material have their own fingerprint. Okay, this diffractogram pattern we call as a fingerprint. What happen if we mix 2 or 3 compound in the mixture? So you can get uh, many peaks appear that representing a different type of uh, mixture compound. So therefore, in order to identify which peak belong to this, which peak belong to this, and which peak belong to this, we need to use the Hanawalt thing, and later on you will see the demo how we use the computerized program like EVA 15 and Expert Score Plus in order to identify each phase or compound presence in the materials. Okay, so like this case, as I mentioned in the globe case, okay, you have the 3D single crystal of the powder, and then in order to identify the pattern of this single crystal, so we need to lay out it as a 2D diagram in order to identify the fingerprint for this single crystals. Okay, so in order to make you more clear, okay, I give you a simple example. Okay, everybody love to eat salt, but remember, don't take too much salt when you eat the food. Okay, it's very maybe harm your health later on. Okay, as you know, what is the chemical formula of salt? Sodium chloride, right? So sodium chloride is a powder form which are solid and crystalline materials. Okay, so in this case, we know this material is salt, but we are you sure this one is salt? Because this white color may be flour, maybe sugar, maybe magnesium oxide, maybe calcium oxide, but the chemical formula for salt is the sodium chloride. So in order to ensure this white powder form is the sodium chloride, we scan the salt sample powder, and then we found that, oh, actually the pattern is here. And then when we use the software, and then when we do the matching technique, so we found that, oh, actually this pattern is matched with the sodium chloride. So therefore, it's confirmed that this white powder is sodium chloride. Okay, so beside the beside the crystalline material for XRD, I stressed out many times in my previous video, even in my instruction, XRD can be measured only for the crystalline materials. Okay. In research, in material engineering research, sometimes the material research engineer use XRD to identify a new advanced material. Sometimes can be polycrystalline, sometimes can be amorphous, sometimes can be semi-crystalline. Okay, that's why when you works in the real engineering world out there later on, okay, most of the company who are dealing with this kind of advanced analysis, okay, sometimes they want to looking the amorphous phase, sometimes they want to looking semi crystalline phase. they can also use XRD emission, because let's say if you use only crystalline material, you will get the pattern as a peak appear here. Okay, the the peak appear here is only for crystalline materials. Remember, the peak represent in this diffractogram graph only reflected to crystalline materials. Okay, so